Okay, hello. We're going to do two quick example problems that I intended to do in class on Tuesday and Wednesday. I did this in period 6. Here we go. Using everything we just learned, find the maximum and the minimum value of this function f of x equals x cubed minus 3x squared plus 1 on the particular interval -1/2, 4. Okay, so this is the absolute max and absolute min. What are we going to do? Well, the first thing that we need to do is compute f of -1/2 and to compute f of 4. In other words, as I was saying at the very end of class, we need to check the endpoints because after all, the endpoints, the absolute maximum and the absolute minimum could occur at the endpoints. Okay, so this is just a brute calculation. Maybe do this first or something so you don't forget about it. Actually, probably the simplest thing to do here computationally is, either use a calculator or synthetic substitution is an option. So I want to evaluate, since this is a polynomial, coefficient of the cubic is 1, coefficient of the quadratic is -3, then the linear term is coefficient 0, and now I'm going to do it, right? So what do I get? 1, then I get -1/2. -3 and -1/2 is -7/2, and if I multiply by -1/2, I get 7/4. Sorry, it's a little cramped. If I add that, I get 7/4, and when I multiply, I get -7/8, and when I add, I get 1/8. So, okay, I'm not positive that was the fastest way, but this is the right answer. So, f of -1/2 is 1/8. Okay, that's good to know. What's f of 4? This should be, even easier. Let's do it. 1, 4, multiply by 4, you get 4, add, you get 1, 4, 4, 16, and 17. Okay, so f of 4 is 17. Alright, and now that we've checked the endpoints, we need to check all other points. In other words, everywhere in the middle. And in other words, we need to find if there are any relative extrema. And for the moment, we don't have to actually determine whether they are relative extrema or not. But the maximum or the minimum could occur at the endpoint or at the relative extrema. So let's find the relative extrema. So now we get to the sort of second step, which is to find critical values or critical points, people call them. What are critical points? They're places where the derivative is 0 or does not exist. Well, this is a polynomial, and so the derivative is going to exist everywhere, so we only need to consider places where the derivative is 0. So, okay, I take this function, I take the derivative, which is easy to do. I get 3x squared minus 6x. That's it. All right, when is this derivative equal to 0? Well, I can factor this as 3x, x minus 2, and setting this derivative equal to 0 for a moment, what we have is that when x is 0 or when x is 2, these are the critical values. Once again, just to clarify, the logic is that I don't yet know whether these are relative extrema. All I know is that if there is a relative max or a relative min, it must be one of these two. Okay, and look, if I just plug in f of 0, I certainly do get, let me do this somewhere else. I get 0, of course. Here, I'll write this, I'll kind of squeeze this in up here. F of 0 is 0. What is f of 2, the other place of interest? Well, all right, let's just do this. One last time. 2, -1, -2, -2, -4, and -3. So f of 2 is -3. And now, what am I supposed to do? I'm supposed to look at these 4 numbers, and these 4 numbers are the only numbers I need to consider when it comes to finding the absolute max. Which of these is biggest and which of these is smallest? So to answer the immediate question, it appears that that is the minimum and that is the maximum. And so let's just answer the question that the min of f on the interval -1/2, 4 is in fact -3. And the max of f on the interval -1/2, 4 is 17. Okay, and so, cool. We're done with the problem. Should we kind of make some sense of this? Okay, it's a polynomial, so, you know, I already almost knew everything there was to say about this polynomial. Let me just try to do this a little differently. Let's see, something like that. So I'm only interested on this graph on the interval -1/2 to 4. So maybe that's 1, 2, 3, 4, or something like that. So what does this function look like? Maybe, you know, not totally to scale. When I plug in 4, I get 17. So way up here at 17 is 1 point. What else? Well, at -1/2, it's 1/8. So I have this very tiny point here, -1/2, 1/8. What else is there to consider? Well, f of 0. What is f of 0? It's 0. And what is f of 2? It's -3. So down here I have -3. This is 2, -3. Okay, so I can probably just put it together what this function actually looks like. What do I know at 0 and at 2? Well, at 0 there's a horizontal tangent, jump, jump, jump. And at 2 there's a horizontal tangent, jump, jump, jump. And so, have I made a mistake? F of 0 is not 0. F of 0 is 1. I'm sorry about that. So that was just wrong from a couple of minutes ago. F of 0 is certainly 1. And therefore, you know, that was kind of wrong. Good thing I caught it in time before I started graphing anything. Something struck me as strange there. So, okay, so that's like 1. So that's the 0.01. And what was I doing? I was drawing in a little horizontal tangent here. And, okay, well, look, I'm not totally sure that this graph looks like this, but I guess I kind of am, right? That, that this is going to be a relative max here. And then somewhere, don't know where, it's going to cross. And then there's going to be this relative min. And then we're up here at 4,17. So, yeah, but actually none of that is really important. What is important is that these two are the sort of candidates for places where there might be relative extrema. And so if my only goal, which was my only goal, was to find the maxima and minima of this function, then I sort of did that already. Okay, that was a pretty easy example. Let's just do one more. You can either kind of like watch this or not, I suppose. Just see something real quick. Oh, I did. That is slightly unfortunate that my face is blocking things. But what if I do that? Is that any better? No. Anyway, well, you can see the answer. Boom. La 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 la. So let's do this kind of quickly. So here's the function f of x equals x minus 2 sine x. Question. Find the max and the min of this function on this interval. Okay, sort of, you know, looking ahead or something. What do I know about this function? Well, let's just first do everything we could do with pre-calc only. I know that sine x is always between -1 and 1. Therefore, I know that if multiplying through by -2 gives me that -2 is greater than or equal to -2 sine x, which is greater than or equal to I multiplied through by -2, so that should be now +2, is greater than or equal to -2x, which is greater than or equal to -2. And, okay, I find this distracting, so let's flip it back. So that's what we got here, -2, boom, by switching the back to be less than signs. And what am I doing? Where is this going? Now I'm going to add x to all three sides of this, and I get x minus 2 is less than or equal to x minus 2 sine x, which is less than or equal to x plus 2. Okay, cool. So, what? It means that my function, I've just proved, this is the kind of thing we did in pre-calc C, that this function is between x minus 2 and x plus 2. All right, so that's kind of a cute little fact. It means that if I was going to go graph this thing, which I do want to do now, then let's see, 1, 2, something like that. Maybe I don't want those tick marks there because it's a sine function, so I sort of care about things on the interval from like pi to 2 pi. So let's let that be pi. Let's let that be 2 pi and pi over 2 and stuff. So here I'm getting ready to graph the so that's the function, right? I suppose, yeah, looking good. And then what do I know about this function? I know that there's this line. Well, this is not going to look so good, is it? I'm regretting my decision slightly here. Okay, well, whatever, too late. Because pi over 2 is like 1.5, so -2 will be down here. So I guess, what are we going to do? We're going to cross through. This is like the line y equals x minus 2. And if I did this correctly, this will be the line y equals x plus 2. Sure. Okay, fine, whatever. That's not so bad. Y equals x plus 2 and y equals x minus 2. And what I know is that my function always lies between these two lines. That's the envelope of the function. Okay, and then what else do I know? I know that whenever my function is 0, whenever sine is 0, it's just going to be whatever x is. So, okay, at x equals 0, it's going to be certainly 0. When I plug in pi here, what do I get? Well, I just get pi. So I almost want like one more dotted line, which is just like the line y equals x, which is going to lie halfway between these. And therefore, at pi, I've now chosen the terrible scale, but I'm just pushing ahead anyway. At pi, the answer is going to be pi. And at 2 pi, the answer is going to be 2 pi. Sure. Okay, and at pi over 2, what's the answer? Well, at pi over 2, sine of pi over 2 is going to be 1. And so what I'm going to get is normal pi over 2, but then, minus So, I'm so disgusted with this, what's happened here. I guess it's not that bad. So it means I'm going to land here, right? Down at the bottom of the envelope. Because, just one more time, when I plug in pi over 2, what do I get? Sine of pi over 2 is 1. So I get pi over 2 minus 2. So it's going to land on the lower envelope. And then when I plug in 3 pi over 2, sine of 3 pi over 2 is -1. So -1 times -2 is 2. So I'm going to be 2 more than 3 pi over 2, which is to say, not on the yellow line, but on the green dotted line. All right, this is just all pre-calc review. Understanding that this is a sum of a sinusoid and a linear function, and finding the envelope and plotting the points and kind of getting the rough gist of it. And if this were now a pre-calc class, I would just kind of do some real sloppy thing now where I would just kind of go like something like that. And that is in fact exactly what we did in pre-calc. Okay, well let me erase that because that's just not good enough now that I'm in calculus. Now that I'm in calculus, I can find where this, and remember, the goal supposedly is to find the max and min of this function on this interval, but I'm also sort of showing you sort of bigger ideas. All right, let's finally do the problem. What is the problem? Oh, I'm supposed to look at the function. I'm supposed to check the endpoints. So maybe we'll do that over here. So f of 0 is 0, and f of 2 pi, of course, sine of 2 pi is 0, so I just get 2 pi. So, good. Could those be the maxima and minima? Well, my picture suggests that no, right? This function is lower elsewhere than at 0, and it's higher elsewhere than at 2 pi. But I don't think the maxima and the minima are at pi over 2 and 3 pi over 2 either. Let's find out. Using calculus, finally, let's take the derivative. What is the derivative? It's going to be the derivative of x is 1, and the derivative of sine x is cosine, so this is minus 2 cosine x. Okay, so when is this derivative? This derivative will always exist. This function is always differentiable. So this boils down to now solving the equation 1 minus 2 cosine x equals 0. And when is that true? Well, it's true when 1 equals 2 cosine x. So when cosine x is a half. When is cosine x equal to 1/2? At pi over 3 and 5 pi over 3. So when x is pi over 3 and 5 pi over 3. All right, what does that tell me? It tells me that these two numbers are the critical values. They're the places that might be relative extrema. And here I can tell you that they are going to be relative extrema. How do I know? Well, maybe I don't know. First, let's plug these numbers in, because we do want to finish the problem. What is f of pi over 3? And what is f of 5 pi over 3? Well, this gets a little bit annoying, I guess, because this is going to be, pi over 3, and then minus 2 times sine of pi over 3. Sorry, what am I doing? Pi over 3 minus 2 sine pi over 3. What is the sine of pi over 3? It's root 3 over 2. Root 3 over 2, fact. And therefore, the answer here is really like pi over 3 minus root 3. And, okay, pi over 3 is approximately 1. It's pretty close. And root 3 is approximately 1.7. So this is 1 minus 1.7. So this is about negative 0.7. That's not so bad. Okay, and what about if I plug in 5 pi over 3? Well, I'm going to get 5 pi over 3 minus 2 times, what is the sine of 5 pi over 3? It's negative root 3 over 2. And so the negatives cancel, the 2's cancel, and we get 5 pi over 3 plus root 3, which is approximately equal to pi over 3 is again about 1, so it's about 5 plus root 3, so that is like about 6.7. And all right, I'm ready to now answer the question. What was the question? Find the max and the min. And the answer is that this is going to be the minimum. This is certainly less than 0. And this is going to be the maximum. Okay, so in this case, for this function on this interval, the maximum and minimum, the absolute maximum and the absolute minimum are not at the endpoints, but are in fact at relative extrema. And now, finally, I can sort of plot these points. I guess I'm doing this in red. So let me go over to pi over 3, which is a little bit less than pi over 2. And we're going to go down to 0.7. Yikes, why does this look so bad? Well, I guess there it is. Boom, 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 boom. And then I'm going to go up to 5 pi over 3, which is a little bit more than 3 pi over 2. And what do I get? I get 6.7, which is so I guess it's going to be like up here or something. So not quite at the on the envelope, but still higher. So this is the kind of the key idea here. Right? This picture is terrible. Of course, we could use technology to make it perfect, but the point is we're using calculus to learn what the function is like. What I now know is there's this point. This works better other times that I've done this. But what I've learned is that pi over 3 and 5 pi over 3 are places where the derivative is 0, which is to say that there's a horizontal tangent. And so when it comes to making this graph, here's now what I know. Contrary to my very, very sloppy graph from before, I can now see that, in fact, the relative minimum of this function is not going to be at pi over 2. Pi over 2 is just a place where it bumps into the lower envelope. But the actual relative minimum is at pi over 3. And it's going to bounce off that horizontal tangent and go up, 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 up. It's going to hit the upper envelope again, but that's not a relative max. The actual relative max is going to occur slightly later at 5 pi over 3. And so here at 5 pi over 3 is going to be a relative max. And here at pi over 3, there is going to be a relative minimum. So here we're starting to see kind of the power of calculus to basically tell us every possible thing we would want to know about a function. And okay, a more systematic way of proving that a certain point is a relative min or max is coming in a couple days. But for now, it's certainly clear that that is a relative min and that is a relative max, and we now know what this function looks like more or less exactly. Okay, goodbye.